Welcome back to NE 630, Nuclear Reactor Theory. So before the spring break, we were discussing the chapter for the long-time behavior of nuclear reactors. And we stated that there is 4 topics that we want to touch. The first one was the feedback reactivity coefficients, and then we stated that we will move on to the long-term behavior, which include the radioisotope buildup in the reactor, nuclear reactor. Then we will look at the poisons buildup in the nuclear reactor and the poisons absorbers, and we will conclude with the burn-up calculation, the fuel burn-up calculation. Then we will have the last chapter will be the types of nuclear reactors. And if we have time, I think we have time for 1 or 2 lectures. Maybe I will just touch on the multi-group diffusion equation, which is not covered in this course. I will not bring it in the final exam, but to expose you to what's going on in the multi-group diffusion equation. So let's start now the topic for xenon poisoning. I hate this stuff here. So we will talk about xenon poisoning. And last time we stated that xenon is produced by 2 separate mechanisms, or 3 separate mechanisms. If you remember, the first mechanism to produce xenon is just from fission. So it's directly produced from fission with gamma xenon. Can somebody tell me what's gamma xenon? What does it mean? So it's the yield or fraction of xenon that's produced from a single fission. So gamma xenon is just 0.00237 in uranium-235. So this is the first time, or the first step to produce the xenon. The other method of producing xenon is produced from the decay of iodine 135, and we will show it to you in a minute. And the third method is indirectly produced from the tellurium 135 to iodine 135 to xenon 135. So as a fission fragment, you can produce xenon. If you produce from the fission iodine, the decay of iodine will give you xenon. If you produce tellurium as a fission product, it will decay to iodine and then give you xenon. So 3 methods of production of xenon. But we knew from last time that the half-life for the tellurium is nearly 11 seconds. And this is why we said we can assume that we will neglect the tellurium and it will be just produced from iodine directly. So to write the equations, the continuity equations for the xenon and iodine concentration, this is d iodine 135 by dt as a function of time. This is just gamma iodine multiplied by sigma fission multiplied by the flux minus the decay of the iodine. And last time we stated that this is the average sigma fission. Then to write the equation for the xenon, this is dE xenon by dt equal to, what's the production for xenon? It comes from fission, so this is gamma xenon, sigma fission multiplied by the flux plus, it came from the decay of what? Iodine, so this is lambda iodine multiplied by iodine of T. What else? Yeah, but we said that the tellurium, we will consider the tellurium is an instantaneous production from iodine from the tellurium, so we'll take off the tellurium, so it will be totally iodine. So those are the two production methods. Then we have to put the decay. So this will be lambda what? Lambda xenon multiplied by the xenon. And what else? Neutron absorption, and this will be sigma absorption for the xenon multiplied by the xenon concentration multiplied by what? Flux. If you want to solve those two equations, you have to solve them simultaneously, of course. So you will start with this equation, yes? And we stated before that sigma average fission multiplied by phi, this is the average what? Average fission rate if you integrate over the volume of the reactor and integrate over time, this will give you some power, yes? So the instantaneous power is average. If you average this, this is average. So this is constant. And then you will have di by dt plus lambda I multiplied by I equal to gamma I sigma fission multiplied by phi. To solve this is a first order differential equation. You will need the integrating factors, and the integrating factor will be just e to the power of minus sigma lambda I, e to the power of plus lambda I, okay, multiplied by t. Then you will solve it, and you will find that it is some exponential term plus this term here, which is the production R, production rate, multiplied by 1 minus e to the power of minus lambda I t. So this is the equation for lambda I, for I of t. Then you will substitute for I of t here, and you will solve this equation to get the x of t. So to do this, gamma I, before we proceed, gamma I equal to 0.0639 for uranium-235, and lambda I is just the decay. Lambda I and lambda xe are just the decay constants. For the iodine 135 and the xenon 135. The half-life for the iodine 135 is just 6.7 hours, and half-life for the xenon 135 is just 9.9 hours. So to solve those equations, you will reach to xe of t, or x of t, if you want to call it, equal to some gamma I plus gamma xenon divided by lambda xenon plus sigma absorption for xenon multiplied by the flux, and here multiplied by sigma absorption, sigma fission, sorry, phi e to the power of minus lambda xenon t plus lambda iodine divided by lambda iodine minus lambda xenon gamma iodine multiplied by sigma fission phi divided by lambda I, all multiplied by e to the power of lambda xenon T minus e to the power of minus lambda iodine T. Or if you want to take sigma fission average phi as a common factor, so this will give you gamma iodine plus gamma xenon divided by lambda xenon plus sigma absorption xenon multiplied by the flux e to the power of minus lambda xenon T plus gamma iodine divided by lambda iodine minus lambda xenon e to the power of minus lambda xenon T minus e to the power of lambda iodine T. You will notice that iodine of T will be I naught e to the power of minus lambda iodine T plus gamma iodine sigma fission phi divided by lambda iodine 1 minus e to the power of minus lambda iodine T. So you have the formula for iodine and the formula for xenon. If you want to be more accurate, this term here is the initial xenon concentration. Anyway, if you start at time equal to 0, fresh, so the initial iodine concentration is 0. So this term is what? 0. And what will happen for the iodine concentration if we try to plot the iodine concentration? You'll notice that the iodine concentration will reach to what? This is I of T, and this is T. It will reach to a saturation value. What's the saturation value? This, if we start with I naught equal to 0, and it's not decaying, if we do not have any initial concentration for iodine, so we are not decaying. What will happen is, when time proceeds, this term will be what? 0, and you will end up with this term. So this is what? This is called gamma I sigma fission average phi divided by lambda I, and we define this term as what? I infinity. What does it mean, I infinity? This is the equilibrium. So I infinity is sigma fission average phi multiplied by gamma I divided by lambda I, and this is what? The equilibrium concentration of iodine. So this is the equilibrium concentration for iodine. Okay, guys? But what if we started with I naught is not equal to 0? Then you will have some term here that is decaying. Yes, and you have this equation. So this will also, you will have some contribution from here, then you will decay again back to the steady state value. Okay, guys? Again, here, if we look at this one, what's the x infinity? So this will go to 0, this will go to 0. So this will be what? X infinity. So X infinity will be what? Sigma fission average multiplied by phi multiplied by gamma iodine plus gamma xenon, all divided by lambda xenon plus sigma absorption xenon multiplied by phi. Yes?
There's a e to the power negative lambda t when I go to 0 in the first term.
Which one?
To 0.
The first term there inside the brackets multiplied by.
Yeah, 1 second. Let me check it. Can you check the?
It's 215.
Hmm? It is actually when you will get the slope equal to 0, I think. So you have to differentiate this equation and equate it to 0 to get what's the plateau, where, because the situation for xenon is completely different from this one. So if you plot the xenon, you will never get this situation, but you will get something like this is the xenon concentration with time. So this is xenon with time, and you will have something like this. So this is once you reach to equilibrium. But let me. Hmm?
I don't know if that's the right spot.
Yeah, but let me check. Oh, there is 1 minus. It's not 1. It's not. I wrote the equation wrong. There is 1 minus this. So it's equation 215, equation 615, page 215. So it has 3 terms even, but the last term is the if you start with x naught initial amount of xenon. So this is gamma I multiplied by sigma fission lambda I multiplied by I, the concentration. This is the tellurium plus gamma I plus gamma xenon sigma fission phi divided by lambda plus sigma absorption, which is this term, plus lambda I minus lambda plus sigma absorption xenon. So I think there is some term I have to include in this equation. But anyway, you return back to the equation 615 in page 215. Okay? But what we want to say here is the following. And this is the most important part for you guys to remember. The most important part for you guys to remember is this curve. You will notice that the xenon concentration in the nuclear reactor will grow up, okay, if you are working on, let's say, on a constant power. If you are working on a constant power. So you will build up an equilibrium of xenon concentration which is governed by this one. So let me Let me make it like this. And this is time. Let's assume that you start clean. So your build up for xenon, you will begin and then build up for some equilibrium concentration for xenon. Okay, guys? Then at certain time, T equal to T1. So here T equal to 0. You start the reactor clean. So you start from 0 because you do not have any xenon concentration. So you start at a constant power. What will happen for your xenon? Your xenon will start building up until it reaches to equilibrium. What does mean equilibrium? Production equal to rate of loss. So d xenon by dt equal to 0. So to get the equilibrium, just equate d xenon by dt equal to 0. So you reach to the equilibrium, then at t equal to t1, you shut down your reactor. Once you shut down your reactor, what did you do for the d xenon by dt equation? So the first thing is production from fission equal to what? 0. Yes? And then production from iodine. So you still have some iodine to decay. Yes? You still have some iodine to what? To decay. So you will have and some iodine to decay, but also you have the xenon decay. Yes? And then you have the xenon absorption, but the xenon absorption is equal to what? 0, because there is no neutron for the xenon to absorb. So I have 0 absorption and 0 production from fission. The iodine decays faster than the xenon. It's 6 hours compared to 9 hours. So I would expect that the iodine will decay faster, and the iodine decays faster means that this is a faster production of what? Xenon. Until xenon will respond, because it will decay after 9 hours compared to 6 hours, then you will notice that the amount of xenon will start also to what? To decay. So you will have an increase because of the what? Iodine what? Iodine decay. Then you reach to a maximum because now the xenon decay kicks in, and then you will have what? You will have what? Exponential decay. Then you will have exponential decay like this. Did you understand? Last year I brought something like this in the exam, but it was fun. It was a power reactor that you have a power reactor working at constant power. Then you drop the power, okay, and work at certain level here. Then you increase the power again to a different level like this. What do you think? What will happen? Exactly the same. Constant power, you reach to what? Equilibrium. If you work enough to reach to equilibrium, you will reach to equilibrium in a couple of hours, let's say. Then you work for this equilibrium, then you reduce the power. Once you reduce the power, this what will happen? You will increase this, and then you will reach to another what? Equilibrium. Now you increase the power. What will happen? You will increase the power, so now the absorption of xenon will do what? Will eat away, because the decay is the decay. You cannot control a physical phenomena based on nuclear decay. It's the lambda I, lambda xe are constant. You cannot control those. Yes? And then what will happen is you will have a dip because of what? Because of the absorption. Then the production from fission will return you back again. So Did you figure out this? So let me show it to you here. Mike, can you just focus onto the book? One more, please, Mike. Okay, that's it. So if you look here, the flux is just phi naught, which is a constant power at P naught. Then it became phi 1, then it became phi naught again. And this is the iodine concentration. So we started at phi naught at the equilibrium concentration for iodine. Okay, guys? And iodine is produced from where? From fission. It's not like xenon. Xenon is produced from fission plus iodine. So the iodine will keep up the xenon concentration. Yes? But for the iodine itself, there is nothing that will feed in iodine. So if you reduce the power, what will happen to the iodine? Will drop. Yes? Because there is no other feeding mechanism for iodine except fission. So you reduce power, you reduce flux, and as a consequence, you reduce what? Iodine. Then you return back the flux again, then the iodine concentration will start what? Will start increasing again. It's not similar for the xenon. For the xenon, what happened is you started at a constant flux. What does mean constant flux? Constant power. So constant power, we reach, let's say, to the equilibrium concentration for xenon. Then the flux drop. When the flux drop, you have another feed. Although you drop the feed from the fission, but the feed from the xenon will give you the increase here. Yes, the xenon, the iodine will decay and give you what? And give you xenon. Yes, and you will have the xenon increases. Then once the decay time of the xenon will get in, you will have this decay of what? Of xenon. Then once you increase the power again, what will happen? You are consuming what? The xenon, and then you will decrease, then you will increase again because of the curve here. So did you look at this power trend? It's I don't know if I will bring it in the exam or not, but last year I brought it in the exam. So this is usually when we were tested for as a reactor operator. Usually if you look at the NRC handbook of nuclear engineering, I think, manual of nuclear engineering, 2 volumes, they are online. The DOE physics manual. I used to have something like this when I was in Argentina taking my license. They tested us in something like this. They would say, here is a power maneuvering situation in a nuclear reactor, what you will do. So you have to understand what's going on here. If you increase the power, what will happen? If you decrease the power, what will happen? What's the consequences here? We knew that the xenon is a very high absorber. The absorption cross-section is what? 10 to the power of 5, which is 100,000. Yes? So when you operate for a long enough time to build the xenon equilibrium situation, what happens when you shut down your reactor? Xenon will increase. Yes? And then start what? There was a power here, then I turn it off. So this will increase, then it will do what?
Decay out.
Decay out. Yes? This is what? Xenon. Xenon number. So the xenon number corresponds to what? Sigma absorption. Xenon is equal to what? Xenon multiplied by sigma absorption of what? Xenon. And this is the absorption cross-section of what? Of xenon, sigma absorption total. And this is equivalent to what? Reactivity induced by what? By xenon. But this is a negative or positive reactivity? Negative reactivity. So I can remove this. And I can plot plot the negative reactivity induced by what? By xenon. Okay. You knew that when you design your nuclear reactor, you have to have what we call excess reactivity in your core. Yes? And you have to have the shutdown margin. What's the excess reactivity? It's reactivity above 0, so that you will keep your reactor critical or supercritical for the lifetime of the reactor before you change the fuel. What's the shutdown margin? Is the reactivity, excess reactivity, the reactivity of the control rod minus the excess reactivity. And you have to have negative, overall negative reactivity. Yes? So let's assume that you have your reactor with the control rod, all the control rod inserted in. Yes? So you will have a negative reactivity inside the core. If all your control rod inside the core, you have what? Negative reactivity. Let's say I want to restart my reactor after I shut down the power plant, for example. What happens is you will have a build-up of negative reactivity inside your core. No matter what you will do in order to remove your control rod to start your reactor again, you will not be able to start your core. Let's assume that in order to your reserve reactivity is something like here. Okay? You will not be able to start your core as long as you are in what? In this location. Once you trespass this point, no way that you will be doing anything until you reach what? You have to wait until you reach what? You reach here. Once your reactivity goes below the reserve reactivity of the core, then you will be able to restart your core again. Okay? And this is if we start, let's assume that we start from a fresh, we operated, start from fresh, operated, then shut down. So here is the reserve reactivity. If your xenon concentration is above your reserve reactivity at time equal to T prime, and this is the other time T equal to T double prime. So this means that if you reach to here and you build this reactivity, for example, inside the core, then you have to wait until after you shut down the reactor. Let's assume that you shut down the reactor somewhere here. You have to wait until you reach to below the reserve reactivity so that you will be able to restart again. This time is defined as reactor xenon dead time. What does it mean? This is after shutdown. This curve is after shutdown. So what does it mean? It means that if you are an operator in a nuclear power plant and you run until you reach to the steady state value for equilibrium, then you shut down your reactor. Shut down, you will start to do what? Increase the xenon what? Concentration, and the xenon concentration will decay. If you cannot start your reactor in this time since the shutdown, if you cannot start your reactor in this time since you shut down, you have to wait until the xenon concentration will decay and get below the reactor reserve reactivity so that you will start again. So let's say that you are working with a nuclear power plant and one of you guys trapped anything inside the control room and you induce a scram. So if you induce a scram, for example, and you want to start, there is checklist to follow and there is lots of precautions to take care and stuff like this. If you will be able to, let's say that this time is an hour or so, if it will take you less than an hour to restart the reactor, for example, nothing will happen. But let's say if it's a problem and it takes you 3-4 hours to figure out what's going on, you have to wait until the xenon will decay below the reserve reactivity, then start your reactor again. And this time is the xenon dead time. Do you understand? So this is what we mean by the xenon dead time. And there is another issue here you want also to be aware of is because of the flux asymmetry. We knew that in the reactor core, if we have a cylindrical core, what's the shape of the flux in the R direction? In the R? It's not cosine. It's a Bessel function, J. And in the Z direction, cosine. So because of this flux asymmetry, the production for the xenon will also be what? Asymmetry. And this asymmetry of xenon buildup will induce what's called xenon oscillation. Xenon what? Oscillation. Because you will have some part of the core has a higher part of the xenon compared to the other part of the core, for example, then you will start to have this phenomena of xenon concentration. Now, let's look for the other Boson that control the reactor again, which is produced from the fission process. But the other one is not like the xenon that you cannot restart your reactor, for example, within a period, which is the time. The other radioisotope is called samarium, and the beauty of samarium is it does not have a decay constant. It's a stable isotope. So the only way, if you reach to, let's say, equilibrium position, yes, the only way that you will eat the samarium, for example, if you will increase the power, what will happen? You will eat more samarium. There is no decay for samarium, for example. So what will happen is, I will show you the derivation, and also I will show you the plots for the samarium. Samarium, the other thing is, samarium is just the absorption cross-section is lower than the absorption cross-section for the xenon. For xenon is 10 to the power of 5 or 10 to the power of 6. For samarium is 40,000, the cross-section. So let's look for the other one, samarium poisoning. So from fission, we will produce Nd neodymium 149. It will decay by beta decay. It will give us americium 149. It will decay by beta decay. And it gives you samarium 149, and again samarium does not decay. The cross section for samarium is just 41,000 bar, and the half-life for samarium, it's 1.7 hour, and half-life for americium is nearly 53 hours. So to write the two equations for americium of time, this is equal to gamma americium sigma fission average phi minus lambda americium multiplied by B of t, and the equation for samarium will be what? ds by dt equal to what? Gamma samarium multiplied by sigma fission phi. What else? There is what? So, sorry, I made a mistake here. The only way that you produce samarium is just from americium. So this should be lambda americium multiplied by what? By B. So there is no fission. There is no fission production of samarium. Okay, minus sigma absorption for samarium multiplied by samarium multiplied by phi. So it's a very simple. The equations are very simple compared to the equation for xenon. So we do not have fission production of samarium. So the samarium is not produced as a fission product. It is just produced from the decay of what? The promethium or whatever, and there is no what? There is no decay for the samarium. If you solve the first equation for the promethium, gamma promethium is just O1 071 for uranium 235, and sigma absorption for promethium is neglected. So B as a function of T is equal to P naught e to the power of minus lambda P multiplied by T. So if you neglect this, sigma absorption, what it is? Yeah, sigma absorption is neglected. But let me check the formula so that I will give you the correct one. Yeah, this is the correct formula. So this is the equilibrium knot, and P equilibrium is just equal to gamma ND sigma fission, gamma ND sigma fission phi divided by lambda P. And then the samarium, the equation for the samarium will be just S naught plus P naught multiplied by, or P equilibrium multiplied by 1 minus e to the minus lambda P multiplied by T. So let's call this S equilibrium, where S equilibrium is just given by gamma ND multiplied by sigma fission phi divided by sigma absorption for samarium. Again, if you look at the same behavior now, like the xenon, here is the samarium as a function of time t, and this is t. Let's assume that you are running at constant power for some time below T equal to 0. Then at T equal to 0, you shut down your reactor. Then at T equal to T1, you start the reactor again. So you have the initial startup. You'll increase your samarium concentration until you reach to the steady state. Then you shut down. Once you shut down, what happened at shutdown? There is no production for what? For bomericium, there is no production. So all will be what? Decay. And what happened for the bomericium? It will be decay, but the decay here will be what? Production in this one, and there is no decay. So you will reach to somewhat increase, and you reach to a constant, because this will decay with time, but this, once it will fully decay, it will reach to what? 0. So all this 0 bomericium will be turned out to be what? Certain amount, certain value of what? Of samarium. So this is why you reach to another value for what? For samarium. Then if you start your reactor again, what will happen? You start your reactor again, you will affect the production of what? You will affect your samarium that's there. So let's assume that you have this amount of samarium. You start your reactor again, you will start eating from this samarium by absorbing neutrons. Yes, but it will take time from the fission to do what? To produce bomericium. So what will happen is you will start decaying. If we will assume that the same power, let's assume that this is the same power. The power was here, then you shut down, then you return back to the same power again. So what will happen is what? You will decay, then you will do what? You will reach to the same concentration as before, this saturation. Okay guys, so I will stop here and continue next time. But again, the main difference between samarium and xenon is samarium does not decay, so it will still stay there. But the reactivity induced from the samarium buildup in your reactor, which is this, is way less than the reserve reactivity inside your core, so you can overcome it and start your reactor operation again. Okay guys? Okay, see you next time.